Good morning, everyone. This is great to see. What a nice turnout. Thank you all for making the time this morning. As I've said a couple of times already, in my book, this is a real treat for us to have Dr. James Jones on campus for the day. I first encountered Dr. Jones in China, at a meeting in China, actually, back in the days of Infuse, when he was with NSF and really kind of leading the charge for food, energy, water systems. We're at a point now he continues to lead the charge as a thought leader in the area and kind of expanding that concept into circular bioeconomy systems. So continuing to have an impact and make a difference, and we're really fortunate to have him with us today. So Dr. Jones is a PhD. Well, he's currently Distinguished Professor Emeritus at University of Florida, PhD out of NC State back in the day, right? And has, as I mentioned, has been very, very active in any number of areas. Spent years, 4 years with the NSF as program manager, involved in really leading the development of food, energy, water systems nexus that has had such an impact. And an impact here on us at the University of Tennessee. He is now retired, living in Gainesville, I believe, or
Tampa.
In Tampa, that's right. And you know, we tried to get him here in November, and this little hurricane kind of messed us up. I was convinced we were having an ice storm today. So the good news, we didn't have that ice storm. Dr. Jones is with us. Thank you all for being here. We're looking forward to learning about his thoughts and insights into circular bioeconomy systems. Dr. Jones.
Thank you, Tim. And thank you for inviting me here to the University of Tennessee. I've been here once before, but it was about 30 years ago, probably before some of you were born, I think, just looking out in the audience. But it's a pleasure to be back, and particularly talking about this, because I think there's a real opportunity for the University of Tennessee, with what I know about it and the activities that you've had with the food, energy, water nexus, and some of the leadership that I've had discussions with, to play an important role here at the university on this particular area. So the title is Creating a More Circular Bioeconomy, and I'll just have to go through these quickly, and hopefully it'll give you a taste of what's being done. I've got both ASABE, American Society of Agricultural and Biological Engineers, logo, as well as the University of Florida logo, because I'm kind of working currently as a leader of a task force for embedding this circular bioeconomy systems idea into the DNA of our professional society, and looking for ways to connect to other professions. And in fact, we are connecting with other professions in agricultural and agricultural sciences, and also in engineering fields. So thank you for hosting me today. I'm glad the weather's nice. It's more like Florida weather here so far. So I'm going to start out talking about some of the societal grand challenges that we face, and some of the thrusts that are being done. And as I've listened to you this morning, I've heard that some of you are working on some of these important thrusts to address these grand challenges. I'm going to say a few words about the current bioeconomy, and then go into circular bioeconomy systems and give you some examples of what we've done so far, starting out in 2019 when I first left NSF and started thinking about this and putting it together and introducing it to the national academies and to the National Science Foundation and to ASABE. There are several initiatives going on internationally and nationally, and ASABE, as I'll point out here, what we're trying to do to build capacity here. Other places are doing quite a bit, at other countries and regions. And then I'm going to end with just asking ourselves the questions, and I hope that you would think about this. How can universities contribute to this really big idea? This is a big idea. And it would take a long time and a lot of effort by a number of disciplines, by a number of efforts, and with education, with research and industries involved in this quite heavily. So, but how can universities contribute to this? The diagram on the bottom is a picture that was drawn by the University of Illinois that I'll say more about later on. This is their depiction of circular bioeconomies, and I'll just talk more about that later on. So some of the challenges to food and agricultural systems is that our bioeconomy is vulnerable to climate change and climate variability. We need to increase demands of, there's increasing demands for biomass, for food, and other resources as well, other products. And we have at the same time limiting and declining natural resources, not only land and water, as we're all familiar with, but also some of the nutrients and also the energy to drive these processes necessary to create the bioproducts that we enjoy. And on top of that, we have between 30 and 50% of the food that's provided and produced is wasted. And that waste happens along the supply chain, and the consumers are maybe as guilty or more guilty than the rest of the supply chain in just throwing that away. And it goes in a landfill. And then degradation of water and soil, nitrogen in the soil, greenhouse gas emissions. And all of these things are happening at the same time. So if we choose to solve only one of these, we may miss the mark on the other ones. And society is really running out of time, I think, to really address some of these problems like climate change. And now that our resources are so limited. And some of my economist colleagues tell me that, one of the real reasons for this is that the natural resources use is really not based on their true financial cost, because you have the cost of purchasing these resources and using them. But then when you don't really pay for all of the residual effects that some of these might have or are having later on down the line. And so they're not really, we don't really respect natural resources as much as we should, I think. So some of the contemporary solutions, and I think some of you are working on these things, is to decarbonize economic activities. And that would reduce the greenhouse gas emissions to achieve net zero or negative carbon, and also contribute significantly to climate change solutions, mitigation. And we need to produce more food and other bioproducts to meet the increasing needs to provide food security. A lot of folks are working on food security. We need to develop biomass products to replace those that are now being used, being produced by fossil carbon sources. We're never going to reduce entirely maybe the use of petrochemicals for some of the products that we use, but we can go a long way. And some of our chemist friends and chemical engineers are showing that now. They're already inventing some of these things. How do we factor that into our production and supply chains for these different systems? We need to produce near zero waste by reusing, recycling, and cascading products to create beneficial uses to society and to the environment. And we need to continually regenerate our natural systems, including soil and water and the biodiversity that we enjoy as well. We have to eliminate environmental degradation. A lot of people working on pollution, environmental pollution and water and soils and so forth. That's also a very important one. And we need to increase the efficiency of natural resources uses and eliminate waste because these are also in limited supply and are also costly, especially if we pay for their true value. And if you look at all of these solution initiatives, and you can probably, most of you in the crowd are probably working on one or more of these solution initiatives currently in your research and teaching and extension activities. So our hypothesis is that achieving a more circular bioeconomy will contribute to addressing each one of these goals. So it's not like we just want to build a circular bioeconomy because we want to build a circular bioeconomy. It's really getting at each one of these. And if taking into account the trade-offs that may exist, if you choose one solution pathway over another one relative to what's happening in these different goals that are listed here and that society has. And so if this is true, then building a multidisciplinary stakeholder partnerships and an alliance that uses the circular bioeconomy principles, and I'll talk about those later, in the design, development, management, and use of these bioproducts will address major societal challenges. So we've got a hypothesis, and we've got something that would show the benefits if it's true. We need to show that this is true and can really simultaneously address some of these things as we go forward. So the bioeconomy, this is something that we've enjoyed, although many people don't call it a bioeconomy, but it's a part of the total economy that's really based on biomass products that are produced by forestry, by agriculture, by aquaculture. So these are products that are put into play by our production systems, but then they also go through value chains, supply chains that provide the kind of products that we need and enjoy in society. And I've got just some images there of the different types. There are many different kinds of bioeconomies that exist, and they're unique almost depending on where you are and what your economy is and what your resources are in the region. I'm sure that Tennessee, for example, is really different from Iowa. Florida is very different from Tennessee. And so you have to fit these within the environment but they can be done in many different ways, and we need to find those solutions. The current bioeconomy, if you step back and look at it, you can say, well, why try to fix it? What's wrong with it? It's highly advanced. It's technologically advanced. And it really has led to amazing food, agricultural, and forestry systems of today. And we're the envy of the world in many respects. We've quadrupled the supply of food and fiber since 1930. And over 22% of the US economy is focused on the bioeconomy. And it employs over 28% of the workforce. And in some senses, we've reduced poverty and hunger to the lowest recorded records, with people working in the bioeconomy to address the food insecurity problems and globally. And there's increasing use of genetics, agronomy, information technologies, machinery technologies. All of these technologies have come together to make this happen. And so we've made this happen, but these gains have occurred without adequately considering the degradation of water and soil and the atmosphere and our ecosystems. And there are many examples of that depending on where you are, and it's happening on a global basis, as you know. And it's also not taking into account the limitations we have in our natural resources. And we're already beginning to feel some shortages of phosphorus globally, and in terms of supplying the nutrients that plants and animals need for their production. And now we've done this also in the past without having to deal with climate change, both from a mitigation point of view as well as an adaptation point of view. So the current bioeconomy is amazing, and I want to make sure that you realize that, but it's not good enough. I think, to meet the challenges of the future. But we can do better. And this is the this is talking about the overall economy, and we got a lot of these thoughts from the Ellen MacArthur Foundation publications and other reports that have come out of in economics and think tanks globally, where it says that the linear economy is the current economic space generally, where the value of products, materials, and resources is maintained in the economy just for a short period of time relatively, and with a substantial generation of waste. And I'm sure you've got a lot of examples of that in your own backgrounds. And a circular economy is the economic space where the value of products, materials, and resources is maintained in the economy for as long as possible with minimal generation of waste. And this is leading us then to the diagrams that are shown on the bottom that shows the inputs to land and water and energy and nutrients and labor and capital all along the supply chain. This represents a supply chain with pre-production, production, post-harvest, transport, processing, packaging, consumption, and waste. Each one of these processes along the pathway has losses in waste. In many cases, individually, they may be doing a lot to reduce losses, because that's an economic loss as well if they lose products. But still, we end up with this 30 to 40% of what we produce being wasted. So circular bioeconomy systems combines the circular economy principles with bioeconomy concepts. And it aims for cascading use of biomass from biological resources using systems approach for economic development. And there are a number of different definitions out there, but they all say something similar to this. And I just saw one from the, DOE has theirs, NSF has one, and many others has one. This is the one that we've adopted here. And these principles are really important to take into account, regardless of what problems that you're working on. The principles of circularity, we've adopted these in ASABE for our initiative as we go forward and embed this into the DNA of our design and management systems that we work on. The first thing is to continue to increase the efficiency of use, efficiency of natural resource use. And that's not just for a single process along the way, but it's for the entire value chain. So if a farmer could be very efficient, and yet if it's tossed away somewhere down the line, it's not really increasing it in terms of the provision of that product. And we need to design out waste and pollution, find ways to use secondary products, not only the main product, find ways to make those as markets, keep materials and products in use, don't toss them, they still have resources there, and that includes food waste, but it also includes textile waste, like textiles that are being used and worn or are discarded and end up in landfills, furniture, and all kinds of other products that are not part of the bioeconomy, but these principles remain true. The three in the middle here were actually proposed by the Ellen MacArthur Foundation, and they're being adopted worldwide. We've added the first one, the increased use efficiencies and the provide economic benefits as the ones that we want to make sure that we're recognized for as we try to increase circular bioeconomy systems throughout our different supply chains. So these are important. This is a diagram that was, let's see, this was presented by Stegman. A circular bioeconomy focuses on sustainable, resource-efficient valorization of biomass and integrated multiple output chains, and with the use of a lot of biorefineries. And that's going to be a theme that you'll see later on too. We need to have more ways of processing the products and byproducts to create the kind of products that are needed and can help replace the fossil fuel. This is a diagram from Stegman, but I think this diagram actually came from DOE originally, where the diagram shows the highest value of biomass products being that are available now that can be produced, and that's pharmaceuticals and fine chemicals that provide, economic value and products. Food and feed are the second highest. Bioplastics and polymers, bulk chemicals and materials. And then on the bottom line, but having lower value, but also very important, are the energy and heat and fuels that these products can produce. So as one looks at taking the biomass that's in the products and using it and repurposing it maybe for other purposes, they may want to take a look at this and see whether the biomass products that they have would fit in which one would they would best fit within in order to not lose them. So I've already talked about the bullet points over here, but the last two I wanted to mention. The first one is setting goals of sustainability, climate change mitigation, environmental impacts. These are important to start with. And then taking an integrated multidisciplinary systems approach is important to really find the right solutions. If any one of our disciplines says, okay, I can fix this, and we go after that solution, well, it may fix part of the problem, but if you're not thinking like an economist or a plant scientist would think, or a soil scientist, it may not fix. It may actually interfere and interact, just like in the food, energy, water nexus. Food, energy, and water interact as well. This is a diagram, and this is primarily to emphasize the value chain, supply chain emphasis. And it shows that it's important for no matter where we're working in this supply chain, we may be working in agriculture and forestry to produce biomass. We need to be aware of what's happening down the line as well to supply the kinds of agriculture and food and other biomass products that really meets the needs of society. And the colors here represent more the bioeconomy, and the gray things represent maybe things that might be done in the just broader economy. But the other idea here is that there are a lot of different innovations that can take place in each one of these sections to follow these principles and address those problems. And I'm not going to try to read through them there, but I think the idea is that this biomass stays in play as long as possible. And there are companies now that are doing this. I mean, there are food companies, there are textile companies, there are new products that are being formed, such as leather, silk, from just growing biomass and converting those through bioprocessing activities. Basically, we need to find ways to close the loops, the resource loops, to prevent these losses and waste throughout the system by adding new processes, capturing that material. And a lot of it has to do with logistics. If you think about food waste, it's happening all along the supply chain, and it's happening with the customers too, the users. This is the diagram that we produced in ASABE to emphasize that it's a system of systems, really. So as an individual, you may be working only on one particular thing, like in the pre-production systems, designing greenhouses or vertical farming systems for for growing food or other crops. Then you may be working in the bioproduction system, biomass production systems like plants or animals or organics. And in the post-processing, handling and processing of food, energy, pharmaceuticals, and other things. And then distribution and use. And then end of use or end of life capture and use of these again, going back into there. There'll always be some waste probably, but we would like to see that down in the low percentage points as opposed to the 30 to 50 percentage points that is happening. We have to get there. So this is a system of systems approach. Not everyone will be working in this whole value chain. But if each one of these does all that it can to understand what the value chains are, and then make their component, their subsystem as circular as possible, then it will contribute to the circularity of the entire value chain. Now, this is from an engineering point of view. Okay, from an environmental point of view, what's happening? There's no environment there. What about economics and policy? There's no environment there. So that we've also come up with this, working with some of the environmental engineers to say, okay, our bioeconomy systems are embedded in natural resources. We not only use them, but we may affect them. And it's these effects that we have to pay attention to more so than we have in the past. And these natural processes are going to go on. We need to think about those and embed this within the bioeconomy systems. And the other part is a social and economic and policy domain. So we have all of these social and economic complexities that add to that, and at multiple scales. It's not just at the supply chain scale, but scaling up from the individual supply chains all the way to the market to meet that demand. So these are actually embedded on top of each other with the idea that this is like I think Tim mentioned this too, it's like a super food, energy, water nexus problem. It's got all of the complexity that would embed the food, energy, water nexus that we had running before, but it also is broader than that. And it really focuses on bioeconomy. The previous NSF program didn't only consider the bioeconomy, and in a lot of cases it was dealing with urban food systems, and it drew the boundary around the urban areas, which is fine. A lot of good work going on there. In a lot of the cases it worked only on production and environment side. But this is a major task, and the systems approach is really needed. In engineering, these are some of the tools that we're using, but maybe other areas as well. Life cycle analysis, techno-economic analysis, circularity indices such as material circularity index that Ellen MacArthur developed. We need one that's more in tune for the bioeconomy now. And decision support systems and models that would represent and be able and allow users to ask what if questions. What if we take this approach? And what if the policy is changed so that we have better enabling policy for creating this kind of new economic benefits and a regional scale or a global scale or even a local scale. So, but there are other technologies that are important, including biotechnology and information technology and machinery technology, which also is being used in engineering as well. This is a picture that came out of the University of Chicago in 2016, just as I was working at NSF. A digital model is like a replica of a real system. So you've got the real system on the bottom here, and then you've got cloud-based analytics above that allows you to predict what would happen to the real system. You can feed data back from the real system back to improve the models or to evaluate different options. And I think this is one of the things that I hope to see in the future, more of these kind of things. This is an engineering tool. A lot of engineering is already using this in their control systems and their production systems. We're not doing that as much in our bioeconomy as we can now and as we should be. So here's some example bioeconomy systems, and I probably should put dairy systems at the top, and I don't even have dairy here, but because dairy is an example where you've got food production going on the farm. You can take waste from the dairy system and put it back on the land to provide nutrients and water, and then that's kind of an on-farm circularity. There are ways in controlled environment agriculture to do this, or in vertical farming, where you can feed the nutrients back or the water back into the system and be very efficient. I mean, some of the vertical farming places now are like 95% usage of the water. Maintaining that much is very, very limited loss in water. But also in the processing and packaging facility, we have food engineers that work on the design of processing systems, taking new technologies that are coming out of chemical engineering or chemistry to embed those into ways that can increase the efficiency and circularity. Cropping systems, farming systems, the biofuel supply chains. I know you're doing a lot of work on jet fuel here at the University of Tennessee, which is fantastic. The poultry production facility, there's a circular poultry production system in the Netherlands, and they're now moving to the U.S. in Indiana and going to be building a similar system there, where everything is really circular as they can, and they don't waste anything. Have multiple products that go away from the production facility. And really the scale of the systems depends on your purpose. And economists typically deal with broader scale issues, but economists are really important to help scale this up to help policymakers make decisions that are important to enable this kind of work, but also to provide economic benefits to society. This is an example that I think Tim maybe have seen this paper that Bruno Basso from Michigan State, myself, and several other people published. One of them was an economist, John Antle. Some of you may know him at Oregon State University. But we looked at a typical corn soybean farm in the Midwest, and we looked at ways that we looked at where the losses and waste are occurring from that farm. And we identified a number of them. And then we said, okay, how can we start reducing those waste and making use of the products that are provided more efficiently as opposed to losing them? And there's a number of those, all the way from producing biofuel on the farm, electricity on the farm, capturing the drainage from the fields, using electrification for the different machinery operations where that's practical, and fertilizers, electrification of the Haber-Bosch process for creating nitrogen fertilizer, synthetic nitrogen fertilizer will greatly reduce the CO2 emissions. It's very energy intensive. And also biotechnology can be used to help other plants convert nitrogen in the atmosphere to nitrogen that the plant uses. There's even some evidence in corn now that can be done. So a lot of these are some of these, and like crop rotations and cover crops, they can be done now because the technologies are there. They need to be improved and tailored to particular systems, but a lot of these are there. Some things can be done maybe in the next 10 years. Others, it may take 15 or more years to really get those going. And that's what we talk about there. And what does this mean from an economic point of view at the farm scale and at the local scale? I think a lot of this work does lend itself well to supporting the bioprocessing and biomanufacturing in rural areas, because that's where a lot of the waste actually end up. And you don't have to capture them and transport them. If you have a big livestock production facility in Oklahoma or somewhere, then maybe there's enough resource that they're producing there that could be used in one of these triangle places there. I know it's for fuel, but it can be also used for fertilizers and maybe other products as well. I mentioned the controlled environment, plant production systems. Energy is a big challenge there because it takes a lot of, particularly the closed systems and like vertical farming. You've got to provide light for the plants, and you've got to control the environment in there. And so it's really energy intensive, although it really conserves resources, including water, considerably. So that's something that's being worked on as well. There are other examples in pork and animal production and processing generally. And one of the things that one of our papers in ASABE dealt with was cellular production of meats. And, you know, just as a concept, these are perspective papers. And I found this somewhere. I think it was an ASABE resource magazine, E.H. Height. I don't know if he's here at the University Department of Biosystems Engineering, University of Tennessee. Is he here today? I didn't know if he'd be here. But what's that? As an advisor, okay. Well, I really cued in on this because this is the kind of thing that I think bioeconomy can really help address, as has been said already. Industries are getting into this. This is an example in California where food waste from grocery stores and local communities are being collected, converted into feed, animal feed, and fertilizer that is being marketed. So this is an example you may want to look at. A lot of this is logistics. You need to have the logistics so that it doesn't cost so much to move the materials somewhere where there's a processing facility, or to capture that and use it without expending so much energy. I'm going to mention ASABE just briefly. I'm kind of running out of time, but we started in 2019, and now ASABE has adopted this. The Board of Trustees approved the plan for embedding circular bioeconomy systems as a central part of the ASABE professional society. And that cuts across all of the different disciplines, and it also enables the connection with other professional societies and stakeholders. And as I told Tim, I'm having to work on the bylaws for that right now, for that entity, but it's we've got a mission and vision. A vision is a healthy planet driven by a vibrant, sustainable, circular bioeconomy systems producing plentiful food, feed, forest products, and renewable resources. That's really what we aim for in the long term. Of course, a lot of work has to be done. We have a number of people working on the task force that I'm chairing from within ASABE and from other professional societies and also industries. Here's some of the other engagements that we're having now, including the national academies. This is a flyer for the CBS Day that we're having in Omaha, Nebraska. On Saturday, we'll have a visit to a farm of the future that is being considered for developing and evaluating and demonstrating circular bioeconomy principles for the different farming systems that they have in their farm. And then on Sunday, we'll have a full day of programming where we'll have plenary sessions with invited speakers from different disciplines. and also technical sessions where we'll have invited speakers as the lead off for each one of those. But then the submission of abstracts is being considered as well. That's still open. I would encourage you, if you're working in this area, to see Laurie Duncan or me, or look online at this place so you can submit an abstract, from this page here. I really would like to see other disciplines there as well, and that includes chemistry, chemical engineering, environmental engineering, economics, and agronomy, and soil science, and the whole 9 yards. One thing I want to mention here, I don't have time to go through all of this, about some of the tactical actions that we're taking to build partnerships and through ASABE, is to develop multi-institutional and multidisciplinary research and education coordination networks. And so there's a group right now working on a proposal for NSF that will organize and connect universities and stakeholders for creating this network. It's not a research network, it's just for helping to expose the ideas and coordinate the research and bring them together into a community that's really contributing to this. And I hope the University of Tennessee would be actively involved in that. Then we're organizing workshops, and these workshops, why are we doing that? Well, we need to find these solutions. And I mentioned before that hypothesis that we have about circular bioeconomy systems being able to address each one of these target goals that are being addressed usually individually by researchers and in some cases industries as well. But we believe that achieving a more circular bioeconomy will contribute to each one of these challenges, for which required knowledge, techniques, technologies, and skills will emerge from the integration of disciplines. And so these will all be interdisciplinary. These are being planned right now. These are the ones that are being planned currently. We've got basically 5 of them where there's already work going on. Socioeconomic value chains, Madhu Khanna has agreed to lead that workshop development, which will involve economists and others. We haven't done this yet, but we want to ask Anu Ramaswamy from Princeton University to be lead on the urban agricultural systems. Again, the boundaries are different in each one of these, in terms of not only in terms of the physical or geographical boundaries, but also what our target goals are. But we think that these workshops can be used to help test that hypothesis. Can these circular bioeconomy principles be used to address these different products? So what roles should universities play? And I'm not going to answer that, but I hope you will answer that. Does education need to be adjusted? I think it does. I think we need to have more of a systems perspective and more holistic perspectives combined with the advancements in technologies that will address some of these challenges, much in the way that it's being done, but doing it in a systems approach. So what mechanisms can be developed or enhanced to educate the public and support continuing education initiatives? And I think, land-grant universities, extension has a strong role to play there. And I hope that they will help bring this to the, not only to the traditional farming population, where a lot of the extension services have been focused, but also to the consumer activities and the industries, some of the new industries that are going on that can use biomass for creating new products. We need to engage in all of these. And then, in an individual university, I think you need to build on the strengths that you have here. And as I look across your industry, your university, you've got a lot going on already. You've already got a group of people who are interested in this. And I think coming together to share knowledge and ask questions. What can you do to help really advance this within your university and within your region and domain of problems that you're working toward, including education and policy too. It's not good enough to say, well, these are not economically viable. Well, why aren't they? What are the policies? Are there policies that help limit that? And how can that be changed so that these will become done? So I think we shouldn't take anything as fixed in our current systems, but really try to make advances. So I'm going to end with this slide, and this is the work that's being done with probably the most advanced university in the U.S. that is in terms of circular bioeconomy systems development. It's the University of Illinois. And they had a number of different groups around campus that were working on sustainability, environmental problems, on resource use efficiency, on biomass conversion to fuels and fertilizers and all kinds of things, but they weren't connected. So they hired a National Academy member, John Reed, who's an engineer, to come in and connect economics with environmental engineering, with agronomy, with crop science and soil science to develop their vision of what would be beneficial to the corn soybean systems in the Midwest. This is the diagram that they came up with. And so if I won't go through it here now, but I'll leave it here and I'll leave these slides with Tim so you can look at them at your leisure and maybe contact the people at University of Illinois. I think John Reed would be welcome to have a dialogue with you. They've already submitted a huge proposal to NSF on this now, and I think some of the aspirations that you might have here could be on developing something that would help you in your region. That region may be the state of Tennessee, it may be a multi-state region, but that's something you have to decide what makes sense and what are the industries that you can support doing this. So let me stop there. I took a little bit longer than I wanted to, about 8 minutes. But anyway, thank you for your attention today.
Thank you so much, Dr. Jones. We do have a few minutes for questions. If anybody has a burning question, Andrew.
I'm not sure if it's a burning question, but Andrew Muhammad with the Department of Agricultural and Resource Economics. I guess one of the things you only sort of briefly touched on is, say, the role of policy in the role of government.
Mm-hmm.
All right, because you think about a lot of these actions, they could either be mandated or in some way incentivized. And it seems to be that you're thinking more of the route that the benefits sort of happen organically and could even be sort of realized in final market prices versus the government stepping in and sort of saying, this is what you must do. So I'm curious, did I sort of get that distinction wrong? Or are you really thinking more about less government and sort of businesses creating all of this on their own?
No, I think to the extent possible, we need to work with businesses to make this happen. I mean, we have to have this as part of the economic system. I mean, it's bioeconomy. It's a circular bioeconomy. So it's got to be part of the economy, and industries and businesses really do that. But there are some policies that, even the past Secretary of Agriculture asked me in a meeting one day, what are some of the policy changes that we need to do to enable our producers and our supply chains to be more economic. So there are those things that I think it's in the mandate of our research and education programs to help identify, along with the businesses that we're working with, and inform them about it. We can't make policies and we can't necessarily even advocate, but you've got to change this policy, that someone else does that, but you can at least inform them about it. And I do think it's going to take both. I think it's going to take an organic process where the industries and universities and advanced research labs come together, and some of that's already happening. But there may be some constraints in some systems that needs to be rethought. I hope that helps. Okay.
Maybe one more question. 2 more questions. 3 more questions.
Coming from the forestry side, in my prior life, I had to not only buy logs across the scale, but get rid of the waste products. We could never get any kind of money for those waste products, to the point where they accumulated so much at the mill that we had a bulldozer working 30 feet off the ground level, trying to spread the pile around. So, and we were connected with the poultry industry and fuel, but yet we never could get a handle on that waste until the mill went down, and then we could kind of catch up with demand. So rurally located industries have a hard time of creating market value for that and moving that material from point A to point B.
If I could follow up with a question myself, do you think that there are new appropriately scaled industries that could be done locally to help pre-process that, and then their products be shipped to some other place for final processing? I mean, I think it is hard in many cases to have more of the industries and biomanufacturing in the rural areas. But I think it would be useful to think about ways of doing that in this circular bioeconomy.
I agree with that. We looked into wood pellets and briquettes for waste material as well. And actually, the University of Tennessee did come down and get some of our spent flakes. But I just throw that out. That was always a really big issue for us. And it did impact the environment when you store that material for long lengths of time.
Oh, yeah. Yeah, no, that's a good point.
Anything else? Well, if not, thank you all once again for being here. You will hear CBS again. And so I would encourage you to kind of think about what Dr. Jones has provided us with today, the information and the thoughts there. A lot of interest building at the University of Tennessee from the system level down. And we're anxious to continue to lead that charge. And so this was perfect timing. Let's thank Dr. Jones once more.